So, very happy to introduce Micah, who is going to be talking to us about bare metal programming from the ground up. Oh, we're working laptop. Cool. Anyway, well, take it away. Thank you.
Hi. Yeah, so I'm Micah, previously known as Ike. So who am I? I worked a while ago, I worked on MicroPython. You might have heard about it. I mostly worked on RF50 support. Currently, I'm mostly working on TinyGo, which is a Go compiler for microcontrollers. I'm the creator and also maintainer. And I also make these blinky earrings and other kinds of jewelry. Yeah, so I'm kind of an electro-witch. For this talk, I'm going to talk about how to program a Arduino Uno and a BBC microbit without using any SDK or whatever, just a compiler, linker, and programming tools, etc., and the datasheet, nothing else. I'm going to talk about the memory map that's listed in the datasheet, how to control GPIO peripherals on microcontrollers, which is quite similar across microcontrollers. I'm going to talk about linker scripts and interrupt vectors. If you know C, that would be useful, especially if you've programmed in Arduino C before. It's actually C++. Then these concepts will be similar, but it's going to be way deeper. So, as you all know, the hello world of embedded hardware is a blinking LED. However, it's not the thing that's simplest. The simplest thing is actually just to turn on an LED. But we'll get to blinking later. So first we'll try to turn on an LED with just compile and linker, nothing else. So the first board I'm going to look at is the Arduino Uno. I think most of you will have heard of it or programmed it. You can see the specification on screen. Most importantly, it has the AVR instruction set. An instruction set is something like x86, ARM, RISC-V. The AVR is one specifically made for microcontrollers. It's 8-bit or 16-bit, depending on how you look at it. And the Arduino Uno comes with the Arduino IDE, but we'll ignore it completely. So, how do you turn on a LED? You set the pin to high, but how do you do that? So the way you do that is by so the way you control hardware on a microcontroller is using registers. Registers in this context means basically a pointer. And normally a pointer points to somewhere in RAM, somewhere in memory, to a variable, so you can change the variable. Except in this case, the pointer points to a piece of hardware. In the end, a pointer is basically just a number. It's a little bit more complicated than that, but basically it's just a number. And you can actually see them on screen here. So the offset here is the pointer address. And on the AVR, like on most microcontrollers, pins are grouped in ports. So 8 pins are grouped in one port and can be controlled together. So, for example, the Arduino Uno has an LED on pin 13. Internally, that's pin B5, so port B, and then the 5th bit of port B. And here you can see 2 registers we're going to use. It's the data direction register and the port register, and you can see the 5th bit here controls this specific pin. So what we need to do, as you can see, the reset value, the default value is both 0. You need to set them both to high. Wait. So for the data direction register, default is as an input. We want to set it as an output. And the other one, the port register, the default is low, and we want to set it high to turn our LED on. So how do you do that? By using C. So this is how you do it in C. You can also do it in assembly or Rust or whatever language. So let's see. What we define here is we take the same two addresses we saw in the datasheet, and we convert it to a pointer. So basically, we take the raw address, which is 24 and 25 hexadecimal, convert it to a volatile pointer, and then dereference it in the macro itself. And then we can use it as if it is a variable, but instead of controlling a real value in memory, it controls hardware. And then in the two lines in the start function, the first ORs the current value with the 5th bit, and the next one also ORs the current value with the 5th bit. And then we'll just insert a loop, so if you flash something, it won't start executing the next code unintentionally, because that's what will always happen. And if you compile it using AVR GCC, we get these 3 instructions, and that's all. So what you can see here is the SBI instruction. It's a set bits immediate, I think. There's one weird thing. You can see there is 4 and 5, but it refers to the actual pointer 24 and 25. That's just an AVR weirdness. But it sets the 5th bit, as you can see here, to 1. And then it jumps to itself. It's a relative jump to the same location, so it's an infinite loop, basically. The full code is like this. Well, it's actually the commands. First, we convert the C code to an object file using AVR GCC, then link it using AVR LD, and then use the AVR tool to write it to a microcontroller, to the Arduino Uno. There's a few things missing here, but we'll come back to that later. And then we can turn on the LED. So that's cool. It's not the original Arduino. I broke it at some point. But it does the same thing. If my screens are working, and my slide stopped working. That's great. Awesome. If it doesn't work in... there you go. It's very confused right now. Anyway, next slide is the... so we want to blink an LED. So what we'll do is we'll... let's try that again. That's... No, the other way. If it would start working now, that would be great. But it doesn't. Okay. Might be working now. Anyway, so, but we want to blink an LED. So we will, what we'll do is we turn on the LED many times and then turn off the LED many times. You might be wondering why we'll do it this way. It's because, so if you would maybe expect to do something like turn on the LED, then put in a for loop, then turn off the LED, and then wait a little bit using the for loop. magic. Okay, we're back. So you might be wondering why we put it inside the for loop. And the reason is that compilers are very good at optimizing. And if they see a loop that's if they see a loop that's that does nothing at all, it will remove it probably. So what we'll do is we put the hardware modification inside the loop, and the compiler is not allowed to remove it because it's volatile. Let's see, and then we get a blinking LED. So that's great. Yeah. But so far we've relied on the default behavior of the linker, which is to put the firmware at the start of memory, and that is not always the case. But in this case, it happened to match. So the way it's organized is it uses. So in the datasheet, you can see the memory map. And in this case, it goes from 0 to 3 FFF, which, if you calculate it, is 16 kilobytes. But as we saw before, it has 32 kilobytes. Why? Because on AVR, flash memory is organized in 16 bits. But most people use 8 bits, so for 1 byte, it's 8 bits, you know. So it's actually 32 kilobytes. Wait, this is not working. Anyway. So we translated to a linker script. A linker script is like a super specific language to basically tell the linker how to lay out which bytes in the object files go where in the final executable or firmware file, which I use sort of interchangeably. In this case, we have two parts. It's memory and the sections. Memory says the flash starts at address 0 and is 32 kilobytes length, as we saw before. And then we'll say to the linker, just copy every text section of the input object file to the text section in the output. The output name doesn't really matter, but it's convention. Also, it's called the text section. That's not because it contains text, it contains binary code, it's machine code. Why it's called text, nobody really knows, it's convention. And if we add it to the linker script, we get something like this. So the T flag adds to the linker script, and I could show the output again, but like it's the same binary, so nothing changed. And the link script, so what we have so far is basically all you need, unless you want to use interrupts. So far, we have basically relied on the fact that code on the AVR starts executing at address 0, and then just continues executing. But the interesting thing about AVR is that when an interrupt happens, it will just jump to a specific location in memory, like these you can see here, and then just start executing code from there. But of course, as you can see, there are only 2 address spaces. It's like 4 bytes between each interrupt vector. So we can't actually put anything there. It's just way too short. So what we actually do instead is we basically make a long list of jump instructions, which are all 4 bytes in length, and then jump to the function that will actually start executing the interrupt. The first one is a bit special. It's the reset vector. That's the one that's executed when the microcontroller resets, so when it powers up or you press the reset button or whatever. And the way we add it is by, so first we had just one AVR GCC invocation, now we have a second one with the vectors. It produces another object file. We link it together, the C object file and the assembly object file, using link script, of course. And then we get well, we would like to get a firmware file, but it doesn't quite work. Why? Because we haven't defined any of the functions that we refer to in the jumps. So the first one is easy to fix. So we have one single function, it's a reset function, we just rename it. And then we get rid of the first one, so that's nice. The rest is a little bit more difficult. So basically what we want to do is we would like to jump to the specific function if it exists. If you define it, then we want to jump there. If not, we'll define that we jump to somewhere else, but just the default, whatever. And that's with these special linker assembler instructions. But it's a little bit verbose. We can do better. We use a macro. This is not a C preprocessor macro, but something internal to the assembler, and we can simplify it a little bit. And if we write this to the microcontroller, let's see, yes, we get a blinking LED. Again, it does the same thing, but a little bit. So here's 146 bytes, which is quite large already, of course. It's still quite small. So that was the AVR, the Arduino Uno. To show how a different chip works, we're going to look at the BBC microbit, specifically the V2. There's two different ones, but most people nowadays use the V2. It has way more flash and RAM, and if my speaker notes worked, I could actually tell how much. But most importantly, it uses the ARM instruction set, which is so you know the older Raspberry Pis, they use 32-bit ARM. Also, older phones from like 10 years ago or something. And this particular, the BBC microbit, uses basically a cut-down version of the same instruction set. But even though it's a lot smaller and simpler, it's still way more advanced than like AVR. So, in part because it's 32 bits. Writing firmware for it is a little bit more complicated, though. We can't just dump code in Flash and expect it to work. We need to look at the memory map, and we can see that Flash still starts at address 0, but data starts in the same address space, unlike AVR, at address 200 and etc. So let's write a linker script for it. It's nearly the same as before, except the length changed because it's bigger. And we added a entry which can mostly ignore it, just to ignore a linker warning. It's relevant on like Linux, etc., but on bare metal you can ignore the entry. Also, we really have to use a interrupt vector. This is the default interrupt vector on the Cortex-M microcontrollers, but unlike on AVR, we can actually write it in C. I suppose it can also be written in Rust, but I don't know that much about low-level Rust. So it contains a list of function pointers and the initial stack pointer. So on AVR, the initial stack pointer is basically the end of RAM, which is usually what you want. But here you have to specify it explicitly. So basically what the hardware does, when it resets, it loads the stack pointer here into the stack pointer register, and then starts executing code from the reset handler. But we have lots of undefined things here, which we can see here. The stack pointer will come back to later. It's an external function. But what you can see here, all functions except the reset handler basically do the same thing as we saw before on AVR in assembly with the set and weak. So basically, we mark it as weak and set the default handler. Like, for example, if the NMI handler is not defined, this tells the linker, just use the default handler instead. And we'll have a empty while loop in here as well, similar as on AVR. And just to try things out, we'll leave the reset handler empty and see whether it compiles. But it doesn't. The stack pointer is undefined. So how do you fix that? By defining the stack pointer in the linker script. So we add the RAM area, which starts at 2000 something, and we define a new section at the bottom. So basically what it tells the linker is reserve some area in RAM for the stack. There are some other people who like to put it at the highest address. I like to put it in a separate section. Opinions differ. But basically what it does is it reserves 4 kilobytes and then tells the linker the stack pointer is located there. Why at the end? Because stacks grow down. So if you push something to the stack, it subtracts and then writes it. So normally an array or a slice or whatever, you append to it and it grows to higher addresses. The stack grows to lower addresses. That's easier in hardware, I guess. And if we try to compile it, it works. We can also write it to the to the microcontroller using OpenOCD. But nothing happens because we didn't define anything. So let's see. I don't have a lot of time left. So we want to turn on the LED. So what we do is we have the row 1. And so this is the 5x5 LED matrix, the schematic. To turn on the LED, we have to set row 1 to high and column 1 to low, and then the LED will turn on. And we can see here the pins. It's pin 21 to 28. On Cortex-M, we use a slightly different way of accessing peripherals. The basic idea is the same, but they are organized in peripherals. So instead of having individual registers, we group them in peripherals. Here you can see P1, P0, and P1, which are instances of the same kind of both GPIO. If we convert it to C, we get a struct, which is really nice to work with. You can also use it as a pointer, which is really nice. So what we do here is we set. So this is a little bit of a weird thing. We set the you have dir, so outset and outclear, and if we write 1 to outset, it sets a bit. If we write a 1 to outclear, it clears a bit. So you write 1, you get 0. It's hardware. So this code is in 3 writes. It sets the direction of both pins as an output, and then sets one of them high. If we try to flash it, we see an Arduino, a microbit that's turned on. So that's cool. And we can use the same reset handler, same trick to blink it as before. Flash it, and then it starts blinking. So that's cool. there are a few things I skipped. Most importantly, global variables. Most larger programs will have at least some of them. They need to be placed in a specific area of memory and need some initialization, but yeah, so this is the basic. So if you get this, you can try one by one to figure out the rest. So that's it. I don't know whether we have questions. Time for questions.
We've probably got time for maybe one question. Has anyone got any questions at the moment? Or otherwise, afterwards, if it's quite
Yeah,
a serious.
yeah. You can. I'll wait outside. So if you have any questions,
Do you have any questions from Signals? No. Oh, you're safe. Cool. How did you start playing with hardware? What got you interested in it in the first place?
Actually, I started studying, and there was computer science, and then we had like one course embedded software, and I just found it really fun to work with Arduinos and stuff. And as a child, I played a lot with like electronics, but then things got complicated, and I gave up. And at some point, I realized I could actually program these things, so I could combine my electronics hobby with my programming. So that's yeah.
That was really interesting. Well,
Yeah.
Micah, thank you very much indeed for a very interesting talk.
Thank you.